Hi, we're going to talk about logistic regression this week. This is chapter 10 from the Shmueli textbook. Logistic regression is very closely related to linear regression that we learned about a few weeks ago, but the main difference is when we want to predict a categorical outcome, such as y being equal to 0 or 1. So we might call it prediction, but really this is a classification algorithm or method, and it is based on a well understood model, linear model, but has a few twists and turns thrown in on it. So what we're trying to do is find a function of our x variables that relates to our y variable, which, as we mentioned just a second ago, is either 0 or 1. And so instead of setting up a linear regression model that says y is equal to some function of the x's, we're going to take another function, a nonlinear function of y, and call that the logit function. And then we're going to model the logit as a linear function of the predictors. And once we have that, then we're going to map the logit function back to the y variable. So here's the basic idea. We're going to say p is the probability of belonging to class 1, and we need p to be a number between 0 and 1 because it's a probability. And if we use standard linear regression and say p is equal to beta 0 plus beta 1 times x and so forth, then that's going to be problematic because for certain values of our x's we're going to get p's that are bigger than 1 or less than 0. So one way around this problem is to use the logistic response function, which says take 1 divided by 1 plus e to the minus of that linear function of the x's. And you can see what happens here as this part goes to infinity, gets very big, then e to that power goes to 0, and you're left with 1 divided by 1, which is 1. And if it gets very big in the opposite direction, negative infinity direction, then we get 1 divided by e to the infinite power, or the limit as it goes to infinity, and that becomes 0. So this solves the problem of making sure that our probabilities are always between 0 and 1. And that then brings us to the next step, which says let's calculate the odds. So given this probability that we just calculated, we can now write the odds as the ratio of the probability of success, or the probability of an event, divided by 1 minus the probability of the event. And you've probably heard the term odds used synonymously with probability, but they are a little bit different. Although you can use them in the same way. You could say the odds of a certain horse winning a horse race, or you could say the probability of that certain horse winning the race. You can use those in the same way, but they do mean slightly different things. So we can go from odds to probability by solving for p, and when we do that we get p is equal to the odds divided by 1 plus the odds. And so with logistic regression, we're going to say the odds are going to be equal to e to the beta 0 plus these other terms. So we have e raised to some linear power, and so if we take the log of both sides, then we have the log of the odds is equal to beta 0 plus beta 1x plus beta 2x and so forth. So this is our linear function of the x's, and we're going to say that's equal to the log of the odds, and this is what we call the logit function. And there are other functions that you can use to do this sort of thing, probit, for example, or complementary log-log, and a few others, but those are a little beyond what we're going to do in this course. So we'll be content for now with using just the logit. The logit function takes in any values of x's that range from, they give inputs from negative infinity to positive infinity, and if the probability is on the x-axis, 0 to 1, then we can write the odds going from 0 to off the chart, goes up to infinity. If we take the log of this function, then we get this S-shaped, sideways S-shaped function that says here we still have probability of success, but now we have the logit. So we just take the log of this thing, take the log, and that gives us that. So there's a lot going on here, and we can better understand by looking at an example. So let's look at personal loans from the Universal Bank data set. The outcome variable is whether a loan is accepted, 0 or 1, and we've got all sorts of different predictor variables that we would like to be able to use to predict the acceptance of the loan. So before we proceed, there's some pre-processing that we need to do. First of all, we need to make a 60-40 partition for training and validation sets, and then there are a few categorical variables, predictor variables, that need to be turned into dummy variables, and here they are: securities account, CD account, online, and credit card. So once we have all that done, we're going to do what you might call simple logistic regression. In other words, we're going to look at just income as our x variable, and we're going to see what effect that has on explaining the probability that someone's going to accept a loan. So we're going to use JUMP to come up with the coefficients. We'll see how to do that later in the next video. But we see that B0 is negative 6.35, B1 is negative 0.0392. So that means our equation for coming up with predicting the probability of a loan being accepted is 1 divided by 1 plus e to the 6.325 minus 0.0392, which is a typo. Somewhere there's a missing negative, because here we've got negative, and then both of these coefficients are estimated as negative. So I'm not sure exactly where the typo is, and we'll just ignore that for now and move ahead. If we have just one x variable, we can get a really good idea of how this is going to look. On the x-axis, we've got income. On the y-axis, we have personal loan. And the line here, the S-shaped line, this is the probability of someone accepting a loan given their income. And this makes a nice picture. This is how JUMP does it. Other data or software packages usually use this sort of function or display. So on the x-axis, again, we have income in thousands, and then the curve is the same, but the data points are represented by either 0 or 1, which is, I guess, a little more accurate than what we have here. Once we have the relationship, we now have just one last thing to do, and that is to estimate the probability of success, the probability of being a 1, and then convert that into a classification based on a cutoff value. And we talked about that earlier. 0.5 is the value that's used most often. And you can go back and look at Chapter 5 to see what considerations you might take into account for changing that cutoff value. So we can continue then by fitting the model to all of the x variables that we might possibly want to use. And we're not going to get into the model choice portion of this yet, but just note that the betas are found using what's called maximum likelihood estimation. It's a little bit different than the least squares estimation we did in simple regression, but the idea is basically the same. And we get parameter estimates given to us in the JUMP output, and there are other metrics that we can look at, like odds ratios, by clicking on the red triangle, which doesn't show up here. I guess it would be up here, or the level above that. And so what we're looking at here is the set of estimates for the logistic regression. In other words, we would say the log of the odds is equal to negative 10.16 minus 0.04 age plus 0.05 experience, so forth. Again, we haven't said anything about model choice or model fit, but these two p-values are a little bit suspect for age and experience, so this isn't necessarily the best model we would use for this. And we can now use this to get estimates of probability for each of the individuals in our data set, and using a cutoff of 0.5 we also get a most likely or an estimate for whether they would accept the loan or not. So we have probability of yes, probability of no. These two things should add up, and anytime the probability is greater than 50%, looks like that's the first one, then this is estimated, this is the first one. These are estimated to be yeses. In JUMP we can see what the estimated equation is for the logit, and basically what I just wrote out. You can see where this probability of a yes comes from. Here's the actual formula, 1 divided by 1 plus exp of minus line yes, or ln yes. This ln yes shows up right here, and this is just the logit function. So before raising it to the exponential power. So if you take 1 divided by 1 plus e to this power, you should get this thing, subtract that from 1, and you get the probability of no. We get several classification performance metrics given to us, including these here, R squared, generalized R squared, and these are kind of complicated formulas. You can actually see the formulas over here. We're not going to get too much into that, but just note that we can use these in much the same way as we did with multiple regression in order to compare models, especially using the validation data set. But what we're really looking for with classification, as discussed earlier, is the misclassification rate on the validation set. That's going to be the one that really tells us how well this model is predicting. And in fact, if we have several models that we're comparing and we choose based on the validation data set, this is a situation where it might come in handy to also use a test data set in order to see how the model is going to perform on new data once we've selected it. We can also look at a lift curve. In this situation, we see that using the model can significantly increase our chances of finding the personal loan acceptance customers. And to remind you how this works, if we look at the first 10% of the population or the data set, we are 7.7 times more likely that we're going to identify someone as a loan acceptor. Multicollinearity is something that we need to sometimes be worried about, and when we're doing logistic regression, just like with simple regression, and if we do have highly correlated variables, X variables, it makes sense to do something about that, either dropping one out or reducing dimensions with things like principal components. When it comes to choosing which variables we're going to use, we have the same considerations to make as in linear regression. So we want to be aware of and leery of our models getting too big, and so keep in mind Occam's razor, which says all things being equal, the simplest explanation tends to be the best explanation, the correct explanation, and so we want to not overfit, and we can do that by keeping our models as small as possible. And one good way to do this is to use forward selection, backward elimination, or stepwise selection, and all those are available in JUMP, just like with the simple or multiple regression. The p-values for the predictors, even though the test statistics are different than what we had with linear regression, are still useful. They test the same null hypothesis, the coefficient is equal to 0, and that can be used to determine whether the x variable should be in the model, given everything else in the model. And that's important in profiling tasks more so than in predictive classification. We don't really care that much about what the coefficients are telling or what the contribution is, marginal contribution of each of the x variables is, given the other ones. When we're predicting, all we want to know is what the final prediction is. We're going to end this video by setting up another example. This is in section 10.4 in the textbook, and I'm going to step through this quickly, and then the next video we're actually going to jump out and run through all of these calculations. So we want to predict flight delays, and we have a bunch of data that tells us whether a flight is delayed, first of all, the carrier, the day of the week, departure time, the destination, the origin, and the weather. So we want to use all these variables to predict delayed, whether a flight is delayed or not. So we're going to partition the data 60/40 into training and validation sets. We need to determine if there's any sort of transformations or recoding of data that we need to do. And then we need to tell JMP a few things to do. First of all, which should be a success, and that's going to be a 1, which you typically wouldn't think of as being a success, but that's what we're going to label it as. We also need to bin the departure times into 1-hour increments, and then we want to use bar charts and heat maps to identify categories that can be grouped together. Once we do all that, we're going to get this output. These are the parameter estimates, and you can see there's a whole bunch of variables that we put in there. We're going to get some output from running this logistic regression model, and what we're really interested in is seeing what the misclassification rate is on the training and the validation sets. And we also will look at the lift curves for both the training and the validation set. And then we'll simplify by getting rid of a bunch of the predictor variables and just use 7 of those. So in summary, we have gone through logistic regression. We have not gone into all of the details into how to come up with the estimates, but there are appendices in Chapter 10 that you can look at that go into more detail, especially when it comes to use for explanatory tasks like the profiling that we've talked about, which is one of the uses that logistic regression is good for, but it's also very good for predicting or classification. And you want to keep in mind that the predictor variables are related to the y variable through a nonlinear function, and that function is called the logit function in this case. There are other functions you can use, probit for example, or complementary log, but this is an example of nonlinear regression, so you've actually done some nonlinear regression once you've gotten to this point. We can still do variable selection like we did in regular linear regression. And finally, keep in mind that logistic regression can be used on categorical variables that have more than 2 categories. So that's all I've got for this video. Look for the next video that goes through Chapter 10, Section 4, and we'll see you there. Send me an email if you have any questions.